All right, so today we're going to start a lecture on electron transport chain. Electron transport chain. So the idea is that electrons are moving. I get my point. Electron transport. So it's a chain in which electrons are moving. So electrons are being transported. You get my point now. Electrons are being transported. So there will be an acceptor. Then that acceptor will transfer it on that person on like that. So the idea behind electron transport chain is that you are transporting electron from one acceptor to another acceptor to another acceptor until we get to the final acceptor. And that final acceptor is what? Is oxygen. So oxygen is our what? It's our final acceptor. So when we talk about electron transport chain, I'm just trying to use the main word to explain it for now. It simply means electrons are being transported from one acceptor to another acceptor until we get to the final acceptor, which is waiting molecular oxygen. Now, if electrons are being transported, what is the source of this electron? What are these electrons? What are these electrons? If you say electrons are being transported in electron transport chain, where do we get the electron from? If you want to answer that question, you need to know that the electrons are gotten from what? From the reducing equivalent, which we know popularly as written NADH. Then, I think it's written like this: NADH plus H. Then also have FADH2. I get my point. These two molecules here are the source of the electron. They are the ones that we feed their electron into the chain. Then the electron will now be transported from one acceptor to another acceptor to another acceptor until we get to the final acceptor. Please get the main story. Electron transport chain. Electrons are moving. We are transporting electron from one acceptor to another until we get to oxygen, which is the final acceptor. Now, what are the source of this electron? The source of this electron are these reducing equivalent, NADH and what? FADH2. Are you getting my point? Now you might be tempted to ask that, okay, if you say these are the source of the electron, where are the electrons here? Where are the electrons here? Now let me just show you now. Let's take this. Let's just take initially FAD. I'm using FAD for example. Initially FAD was just FAD like this, right? Then it acquires 2 hydrogen. Is that not so? So that's why we now write it as FADH2. These 2 hydrogen here, this H2, hope you know electrons is in this place. We all know that one hydrogen atom is equal to waiting 1 proton plus 1 electron. Are you get my point? So that means 2 hydrogen. So if we have something like H2 now, it will be what? 2 proton and what? And 2 electron. What am I trying to tell you now? In this FADH2, they are waiting 2 protons and what? And 2 electrons. So in like manner, in the same place too, there are 2 protons and 2 electrons. I get my point. There are 2 protons and 2 electrons in this NADH plus H, and also there are 2 protons and 2 electrons in this FADH2. Are you getting the idea? Electron transport chain simply means you are transporting electron from one acceptor to another acceptor until you get to oxygen, the final acceptor. What are the source of this electron? The source of this electron are from waiting. This reducing equivalent, they are the ones that will feed their electron. So anytime FADH2 want to enter the chain, you are expected to see the movement of 2H plus and 2 E minus. That is 2 proton and 2 electron. Are you getting the idea? All right. If you understand up to this point, I would have loved to show you how NADH is written in this form and not in this form like NADH2. Let me just show you that quickly. Why we don't use to write NADH in this form, but rather we write it in this form? Why? So let me just answer that question. Normally, NADH is written as the normal form of NADH is written NAD plus. And you know that these molecules basically they will take 2 hydrogen, abi? So if we take 2 hydrogen, see 2 hydrogen is something as, let me just say H2, abi? This is what it is going to take, right? This thing is equivalent to what? 2 proton and what? 2 electron. Do you understand? Let me just bring it out again. These two protons, same thing as H plus, right? This electron is waiting E minus, E minus. Is that not so? Now, if NADH plus, we take these two things, we take everything here, which is equivalent to this, right? If you take the, okay, let's say this minus here, we cancel this plus. I get my point. So what are we now left with the NADB? Then if I take this one and this, hope you know it's equivalent to one hydrogen atom. So I will just put it as NADH. Then what is left there? She is H plus. So now that's why we used to write it as NADH plus. So the whole concept behind this, is that since electron transportation simply means the movement of electron from one acceptor to another acceptor until we meet with oxygen, which is the final acceptor, what are the source of this electron? The source of this electron is basically from NADH, which is written as NADH plus H plus. You get my point? Why FAD is written as FADH2. So these are the guys that will give us the electron. Yeah, start transferring the electron. Start transferring the electron. Do you get the gist? All right. What is the site? What is the site for this electron transportation? Where does it occur? Where does electron transportation occur? What is the site of electron transportation? What is the site of electron transportation? It occurs in where? It occurs where in the matrix of the mitochondria. Am I correct like that? No. It occurs where in the inner mitochondrial membrane. Inner mitochondrial membrane. Inner mitochondrial membrane. This is where it occurs. Inner mitochondrial membrane. Okay. We all know that the mitochondria is double membrane structure, double membrane organelle. This is the first membrane. Then the second membrane, which is the inner membrane, is now thrown into fold. It's thrown into fold, right? So it's thrown into fold like this. I get my point. Now your Krebs cycle occurs in this middle, which is the matrix. This is the matrix. Here is the inner membrane. Here is the waiting outer membrane. This inner membrane is thrown into fold. I think they do call it crystal. I get my point. So this is the fold. It is in this inner membrane that is thrown into fold. That is where your electron transport chain occurs. It is in this place you are going to see your electron carriers, which will be the one to be accepting the electron, transferring the electron, accepting, transferring, accepting, transferring. I get my point. Krebs cycle occurs in the matrix. Electron transport chain occurs in the inner mitochondrial membrane. Do you understand? All right. If you get to that point now, I believe we can now go into the electron transport chain proper. But please, I like repeating it. Electron transport chain simply means you are transporting electron from one acceptor to another acceptor until you get to oxygen, which is the final acceptor. But the question I would love to ask is now, why are you transporting the electron? Why? Why are you transporting the electron? We've known that electron transport chain, transport of electron from one acceptor to another acceptor to another acceptor until we get to oxygen. The question is why? That is the big question. Why are you doing it? Why are you transporting the electron? What is the purpose of that? Now, the reason why the electron is being transported is so that we can trap energy from it. You know, when electrons are moving, it's more like energy is moving. I don't know if I get my point. So just picture it as current. As current is flowing, it simply means energy is flowing. I get my point. So as the electrons are being transported in the inner mitochondrial membrane, if you are wise, you will trap energy by pumping proton from the matrix of the mitochondria to the intermembrane space. Are you getting it? What am I trying to say? As electrons are being transported in this inner mitochondrial membrane, what we do, we pump proton from the matrix. There are a lot of protons in the matrix. So we pump those protons from the matrix to the intermembrane space. To the what? Intermembrane space. Do you get that one now? Hope you got that one. All right. So we all agree just now that electron transport. I'm sorry I'm repeating it. I want you to get the concept because once I go into the main stuff, which is the component of each complexes and all those stuff, I don't want you to be confused. So as electrons are being transported, we are using the energy of that transport to pump proton from the matrix of the mitochondria to the intermembrane space, such that we are not letting those protons to reverse back again. We're not going to let those protons to reverse back again. Rather, the protons will create a gradient in this inner mitochondrial in this intermembrane space here. So the whole proton that you pump will create a gradient. The proton will generate a gradient called chemiosmotic gradient. You get my point now? It is this chemiosmotic gradient you are going to use to phosphorylate ADP to ATP. It is this chemiosmotic gradient you will use to phosphorylate ADP to what? To ATP. So let's get that main idea. That is what we call a chemiosmotic principle. So the idea behind the electron transport chain, like if somebody asks you electron transport chain, what does it mean? Simply means electrons are being transported in the inner mitochondrial membrane until we get to oxygen, which is the final acceptor. Why? Why are you doing that? Simply because you want to pump proton from the matrix of the mitochondria to the intermembrane space. When you pump the proton, what now happen? We refuse to allow the proton leak back into the matrix. Rather, we create a gradient such that when we create this gradient, the proton will begin to rise. Let me use that word sharp, but this gradient you've created will make the proton to accumulate in such a way that they will only pass through a channel back to this matrix, and that channel is what we call complex 5. That channel is what we call complex 5. And as it's passing through that channel, it is going to convert ADP to ATP. So that's how we form ATP. Electron transport chain. Transport of electron from one acceptor to another occurring in the inner mitochondrial membrane. As the electrons are transported, proton is being pumped from the matrix of the mitochondria to the intermembrane space, such that those protons will not be allowed. You will not allow the proton to move back. So the proton is not waiting and not allowed to return. I get my point. They are not allowed to return. You won't allow them to return back through the same process. Rather, you will create a gradient called chemiosmotic gradient. Chemiosmotic gradient. Chemiosmotic gradient. Okay, so you create a chemiosmotic gradient. The proton will only pass through one pore, which is the complex 5. Do you get it to that point now? Now, if you get this general idea about electron transport chain, thank God, that means the thing is very, very easy. You get now, it's very, very easy. All right. We all agree that in the electron transport chain, electrons are transported. Now, as electrons are being transported, we pump the proton, blah, blah, blah. We've discussed those ones. Now, there's one thing you need to know also, that during the course of this transport, there are 4 complexes that the electron will be transported across. There are what? 4 complexes. We have complex 1, complex 2, complex 3, and complex 4. So there are how many complexes? There are 4 complexes. What do I mean by complex? It's more like a series of transport protein. They are all together. It's more like a complex enzyme. So there are 4 complexes. We have a complex 1, we have complex 2, we have complex 3, and we have complex 4. Okay, so I think I will stop here for now. In the next video, I will review to you what are the components of each complexes. Then once I tell you the component of each complexes, then I will tell you how the electron is being transported. What are the source of this electron? Let's just revise a little bit. We say the source of this electron are from what? From our reducing equivalent. So these are the guys that will start the chain. They will start the chain, okay? They will start the chain. All right. So there are 4 complexes, complex 1 to complex 4. And also there's also another one called complex 5 actually. There's another one called complex 5. But complex 5 is the one that is responsible for the phosphorylation of ADP to ATP. So when you are talking about electron transport chain, we usually call only 1 to 4. But when you now call the phosphorylation, that is for what? Complex 5. I will say that again. Complex 1 to 4 is for the transport. But when you now want to phosphorylate, ADP to ATP, you will use complex 5. So complex 5 is that pore in which the proton will enter back into the matrix. So the gradient of that movement will be used to convert ADP to ATP. I hope that is clear. So in the next video, we'll talk about complex 1 to 4. We open the entire complexes, tell you what is present there, cytochrome, iron sulfur protein, and the likes, everything I will show you. But in complex 5 also, we also look at complex 5 in the next video. Then subsequently, we are going to look at the main transport, like we draw the whole structure of the chain, how you are going to write it in exam condition. Then we'll look at the inhibitors of the chain. I get my point. The inhibitors of the electron transport chain, all those ones. We'll look at everything. So in next video, this is what I'm going to look at. All right. Thank you.